Today, we are very happy to introduce Mauricio Elizalde from Autonomous University of Madrid, Spain. He'll be talking about intertemporal cost-efficient consumption. Okay, so please.
Thank you very much for the introduction, and thank you for the invitation to this virtual seminar. And well, I'd like you to present this topic, which is joint work with Stefan Storm from the Worcester Polytechnic Institute. And well, I should mention that this is one of the main topics of my thesis. And at the end, I will describe some open questions that we will try to solve. So if you have questions or feedback, I will appreciate it. Okay, well, let's start with the problem. The main problem is how to make an optimal consumption investment given a budget. So to solve this problem, as a first approximation, Sharp et al. Developed an interactive tool called the Distribution Builder. They use this approach instead of using utility maximization because utility functions are hard to measure in practice. They couldn't take the actual preference of people. And they say, well, let the agent directly choose the desired distribution of the middle of the words that could be reachable given an initial capital, which is the budget. Well, they say that a classical utility-based portfolio optimization starts from the budget, prices, and preferences as inputs, and then the investor as an output choose the most desirable distribution that is the one that maximizes his or her expected utility. And well, they say, well, assume that investor has a target distribution about his or her wealth, and we can observe the budget and prices. So we have a budget and prices as an input, but we change the distribution, the wealth distribution, from the output to be an input. And then we have as an output the investor preferences. So let's talk about how did they do it. Well, they did this with the approach of a retirement perspective. So in the paper, they have an explanation about how this interface of distribution builder works. And as an example, obviously, this could be more general, but in this case, they ask people, well, you have a little blocks that you will arrange. It's like a Tetris, and each block represents the percentage of the pre-retirement income. So if you see the y-axis is from 0 to 200, and each person can arrange the blocks. That it's about 40 blocks that they have to arrange. And there's a reference point that is 75% of the income. and they are given that the row 75 is the risk-free reference. So if you can put all the blocks in the 75 reference, and you will get the 75 of the rate of retirement per retirement income as sure risk-free. But then, if you want to enter to this stochastic game, you arrange all the blocks with well, wherever you want, but with a restriction. Because if there's no restriction, one can say, well, I arrange all the blocks in 200 row, so I can a bigger outcome. But there is a cost meter that computes the cost of the strategy of your arrangement. So you have a budget that is 100, that represents 100%, and you should arrange the blocks so you can not well, you have the limit of the budget. So this is an example of a log normal distribution about how a desired well distribution on a person. And well, I should mention that it's not our goal in this case, but they have a button here that if you submit it, you have a realization of this stochastic game, and it results in one block. So you can play with it. Okay, the math behind this is that in one single period approach, a person through the distribution builder specify desired preference for his or her retirement income, and then we represent the preferences with the well distribution f of x equal to 1 over n, where x, well, for multiplied by the number of the outcomes of random variable x in the n states respectively. The budget, that is the cost of this problem, is the expression of the cost efficient, that is the minimum cost of the problem, that has this expression, that is the minimum x that achieves, the minimum random variable x that achieves the minimum over all random variables x of this expression, that is the random variable x multiplied by the price kernel psi. And diving provides that the antimonotonic property is sufficient for cost efficiency. That it means that the random variable psi here and x should be arranged in an opposite way. That means that if I have two elements of omega, and I apply the random variable x and y, I say that they are icomonotonic if this multiplication is bigger than 0, and anticomonotone if x and minus y are comonotone. So it's like the correlation. So we can think that anticomonotone is that they are all uncorrelated. Well, given this approach, we ask ourselves how we can generalize this approach to have an intertemporal cost-efficient consumption. So the previous approach is one for one time. And well, as a naive approach, we can let the investor specify the desired distribution of every consumption period and iterate the terminal market approach, arranging every distribution to be antimonotonic with the price kernel. It means repeating the previous argument n times, thinking about n as a number of periods. But well, that's economically not sensible, as this approach doesn't capture monotonicity between distributions. And we are concerned about the dependency structure of every distribution in the consumption. So we propose a sophisticated way to add that dependency structure via copulas. Well, I present the copula we will use, that is Clayton Copula. That is an Archimedean copula that is very useful to model the dependency structure between random variables, because they have only one parameter, alpha, that is highly bigger, more tractable than, for example, in Gaussian distributions to compute bigger covariance matrix. So this parameter alpha is introduced in these closed expressions. I must mention that Archimedean copulas are copulas that have, well, in practice, a closed form expressions. And well, this copula depends only in alpha, and let me show you in a picture how it looks like with two random variables. So if I let alpha be closer than -1, we have an anti-correlated structure between random variables. Here, y-axis and x-axis represents each one random variable. If I let alpha be close than 0, we have we don't have correlation structure. And if I let alpha tends to infinity, I have a bigger and bigger correlation, positive correlation structure. So you can visualize here that from alpha equal to 15 or more equal to 100, in 100 I have almost perfectly positive correlation structure. Well, before I continue, we demonstrate that what we've done already exists. It means that there exists a random variable that achieves a desired distribution when the investor chooses her or his joint consumption distribution infinitely many periods. So that that makes sense to have to do this problem with infinitely many periods. For this, we choose x1 to xn, a random vector that these x variables represent the consumption. And well, we let g be the cumulative distribution function of the sum c. And well, c is this represents the sum of my random vector, the elements of the random vector, and that's the distribution I desire. So if I let set tilde be a random variable that has the same distribution as set, that is the distribution I want, we show that there exists a random vector such that the sum of that random vectors achieve the distribution I want. So what I mean with this is that if I have set as an input, I can found an random vector of x tildes that achieve that distribution in their sum. And well, having this, we construct the optimal consumption algorithm, in which we assume that the financial market is free of arbitrage. We consider a small n states of the market, and at each time t k, within of the state prices of omega I from I equal to 1 to n. And we assume that there exists a price kernel for each time. So we can price x, a random variable x with expected value of the random variable multiplied by the price kernel. So the optimal consumption until horizon time satisfies this equation. So in this equation, we can see the sum of the random variables x, k that I denoted at C in the theorem. And since that distribution, it's achieved at time at the nth time, I use the finite time kernel. So I price that sum with this kernel. So for all possible random vectors, I choose the one achieves the minimum cost. And well, is not only the problem is not only to find the minimum one. So I give an extra I mean, we have another restriction that they have to have a dependence structure via a copula. And well, we see how we can achieve this. Well, we have 3 steps for the algorithm. We generate first in small n simulated values of the stepped process. And then we simulate the observations of the consumption distribution. And this is in general. In the next steps, we can, I give an example that we use a step-based process in Black-Scholes model and Clayton Copula, but let me tell you in general how this can be done. So we simulate the state price process, we simulate the observations of the consumption distribution. First, we generate the n simulated values of capital N correlated vectors. Here I call vectors C, C1 until Cn. And then we compute the x vector, and that vector fulfills that they have the every distribution I gave to every step. I mean, not only I have the dependence via copula, but for each time I have a desired distribution. That is, this is the way this is connected to the distribution builder rate, because F stands for the distribution I want to achieve. And in this case, for simplicity, to give you an example, I assume that in every time and in every period, I want the same distribution. And I give that example for a log normal distribution. As I already mentioned, I can compute from here the sum of x k, and to have this arrangement. In every row, I have every x random vector with n observations, and for each one I have the sum. So this represents the sum in each state of the market, and from each state I have the price kernel. So from here I construct set star for the elements of set order in an increasing way or decreasing way, but I have to choose a way that is antimonotonic with the started price kernel, so I achieve the minimum costs. So we arrange the sums to be antimonotonic with the last column, and that's our solution. So the new arrangement of the variables have the same joint distribution and a lower or equal cost and respect to the original ones. So the minimum is achieved with this set star constructed by the antimonotony restriction. And okay, let's give an example. If I work in the Black-Scholes model with Clayton Copula and choosing a consumptional log normal distribution with parameters which I call mu log and sigma log from every period for each, I have that. The unique state price process have this expression where the Sharpe ratio is represented by theta. And well, the important thing about this expression, that is, if using the first factor, is that the state price process is decreasing respect to the stock. So I can see the shape of the psi, and what it matters is that time capital T. So this is of the form constant over st capital T, where EC is a positive constant. So if I choose the S being a log normal, and that is increasing, well, it's enough to figure out that the price vector is decreasing, and if I multiply it in that way, they are antimonotonic. Well, for the example, I set n equal to 10, and for negative values of alpha, the standard deviation of the chosen log normal distribution is inversely proportional to the costs, and for the positive value, relation is proportional. We show this. I show this in the next slide. That is this. Okay, what have we here? Here I plotted the relation between the cost, that is here, the parameter alpha, that is the parameter of the Clayton Copula, and the standard deviation of the log normal distribution. This is the standard deviation, but not the sigma parameter, just to be clear. And with these parameter markets that are standard parameters, we can realize numerically that for negative values of alpha, the cost is bigger and for positive values on alpha, the cost is less. Even we achieve a minimum around after equal to 15 or 20. Here in this picture, maybe it's not so clear, but when I move it, it's more clear. And well, what can be said about this? Well, it's more costly if I have a negative dependency structure in my consumption, that it says that, well, if I consume a lot this time, I will consume less the next time. That is costly, that this says that this example. So what it says that in the opposite way, that if I consume I don't know, X amount in this period, a similar amount in next period should be consumed. So that's the way is less expensive. Well, we perform which we call cost-efficient frontier, and that is a plot of the relation of the standard deviation and the expected value per period. So we have a budget of 1,000, and we have 10 periods. So roughly speaking, we have an expected value per period of 100. So that 100 is risk-free. So entering this stochastic gain, which be the expected return of per period, well, I have it here. And obviously it's increasing if I increase the risk. And I could show the case alpha equal to 15, but in that case is a straight line. For very big values of the standard deviation, it started to get horizontal. So I choose these values of alpha so you can see the shape. And well, this is only to visualize how this relation works. And this is good information about how an investor choose, or how he or she is willing to risk to have an expected value, right? Well, I move to the part of the how can we hedge this. And well, we construct a hedging strategy to replicate this cost-efficient consumption problem. And well, the first phase is to find a measure Q, so that the discounted price process is a martingale. And I let the node with delta the units of stocks outside the units of the bonds we need to hold to make the replication. For the Black-Scholes models, we have that this change of measure is good. That is, I use the parameter that is equal to the this is the Sharpe ratio. So the measures, the original measure P and the risk neutral measure Q are related by in this random nicotine derivative, and that's why that the price process on the Black-Scholes model I stated before have this shape where A is all the constant I showed you before. So on the basis that Z star is antimonotonic with the price kernel, as I told you, the price the stock price in Black-Scholes model is anti-monotonic with the stock price process. So for a moment, let's see this part of this equation and see that we take here the the distribution of psi, and we think about this about being a random variable. This is uniform distributed. So if I apply this little trick, that is, I take one and subtract a uniform random variable, I have another uniform random variable that is anti-monotonic with the Stifler process. And so this expression have the same distribution of Z star. So that's the way Z star has a distribution that is anti-monotonic with step-by process. And since I found that S, that is stock, is already anti-monotonic, well, just only I have to take into account to compute Z star. Well, having this in mind, I defined to find the delta psi parameters a new random variable E that is the expected value until time t of Z star. And let's assume that E of t is Malevin differentiable and meets the Clark-Open representation formula. So here we have that phi is the expected value of the Malevin derivative of ET, and we use the relationship of the dynamics of the stock under the Q measure to find that the solution of ET with applying the Clark-Open representation formula have this shape where we define delta as phi over sigma t to find the number of shares of the stock I need to hold, and just only take the subtraction ET minus delta ST to find the units of the bonds. So if I apply this to a log normal example, we find that if we take the representation of the distribution of the log normal, and we have that Z star have this shape, and which this is important. The shape, it's the only important thing that is that could be represented as constant multiplied by ST to the sigma log over sigma, where sigma is the Black-Scholes parameter and sigma log is the log normal distribution parameter. And therefore, I can find a closed expression for ET, and taking into account the derivative, the Malevin derivative of ST is sigma ST, I have that phi have this expression, and the hedging positions have these closed form expressions. So, well, if you have a question, please stop me about if I going quickly. But well, I only skip the details of the computations. But the idea is that okay. Well, we try to do it not only for the Raxos model, but for the CEV model. And this is one that leads us of one of the open questions, because this is not fully finished. And well, let me introduce this part. So in this part we assume ST follows a constant elasticity of variance process with the dynamics, with these dynamics, where the important parameter here is beta plus 1, and that is the exponential of the stock. And let's observe that if v is equal to 0, CEV model reduces to Black-Scholes, and if is equal to -1, this part cancels out, and we have the Bachelor model. Well, to have the Q measure for the stepwise process, we use for a paper of Mijatovic that we can use this density process that is a Dunlian's depth exponential, where we can see we again use the Sharpe ratio. But we have integrals of exponents of the stock and in this it's a little tricky to handle it. So to find the distribution of that random variable y, we take the logarithmic version, and well, we consider the moment generating function to find the distribution and make some computations. We realize that if we again have a Dunlian's depth exponential, we can define a measure here. Let's see that this is an expected value of this exponential, and we have another exponential. So in this part, we arrange the exponential to have a new measure inspired in Q, such that the expected value of this is 1. And that Q measure, we name it as Q lambda measure, because it depends on lambda, and is nothing else, the parameter is nothing else that lambda times the Sharpe ratio. So we can rewrite the expected value, well, the moment generating function, as the expected value on the new Q lambda measure of what remains of our computations. And this, what remains, it's something in terms of lambda multiplied by a quadratic version of a CEV process with parameter minus beta plus 1. And we can choose any drift to solve the problem. So for convenience, we take S tilde with no drift. So what is S tilde prime? Well, to solve this, we let B, that is a function of S tilde prime, be the instantaneous rate of S tilde prime. And we express BT as a quadratic three-halves process. And why? Well, in a paper published by Son and Carr, we have that they gave a Laplace transform of the quadratic variation of this kind of process. So this is to apply that theorem and have the Laplace transform of what I told you, that is something multiplied by the instantaneous, the quadratic version of the CEV model. And well, this is the the expression where HT it's in terms of the stock price at times 0, alpha S depends on S, and beta gamma S depends on S and beta also. And we have that this is a convolution, the hyperconfluent hypergeometric function. So altogether, and well, this is in terms of in gamma functions also. And our open question is how to handle that expression to find the state process distribution and perform the intertemporal cost-efficient consumption example. But the theory reaches until that. So what we have to do now is in practice. And once we have that, we can ask ourselves how this could be generalized, not only to have in periods, but to have infinitely many periods. So we are talking about a continuous version of the cost-efficient consumption. And the issue here is well, we have not a sum, but an integral of all x and stepwise process and all times. I have a typo here, is from 0 to capital T, but I have two restrictions. I remember that I have to reach this expression, I have to consider that X should be antimonotonic, and we show that already antimonotony can be reached with the uniform random variable trick. But we have to add to that a copula, a dependency structure in the random variables. And that could be done using a result from Julia Di Nuno et al., where they have studied the copula measures. So they gave a dependent structure to a random variable in continuous time. More, we have to figure out how to do that two restrictions fulfilled at the same time, because in the case, in the discrete case, in the algorithm, remember we first construct from the copula the random variables, and then we arrange them to be antimonotonic. So I think it's not easy to do that continuously, and we have to figure out how to do it to fulfill the two restrictions, then the monotonicity and the dependent structure restriction at the same time. Let me thank you. And if you have questions, I will be happy to try to answer.